Good evening, everyone. Welcome to the webinar today by MSA, which is conducting the seminar today. There's a short disclaimer on your screen that I can just quickly read out. The information provided in this webinar is for general information purposes. While we try to keep the information up to date and correct, there are no representations and warranties by ISHRE for the completeness, accuracy, reliability, suitability, availability, and respect to information, products, and services that you'll be hearing about. We do not guarantee or declare that the information in the webinar is accurate or correct, and we're not responsible or shall not be held liable for any errors and hiatuses in the content of the webinar. The speaker's views will be discussed today and do not represent the views of ISHRE. So let's begin. Next slide, please. So today I'll just quickly introduce Dr. Jason Shiliday. He is the HVAC sales manager for MSA, and he has a PhD in environmental technologies from the Brunel University in London. He has over 15 years of experience in HVAC and refrigeration in Europe and the Middle East, and he's considered an expert in and specialist in refrigeration gas detection. MSA, the company, is about $1.35 billion company, headquartered in Pennsylvania, has operations in US, Latin America, Europe, Asia, and has about 5,000 employees. And one of the main products of this company is self-contained breathing apparatus, fixed gas and flame detection systems, and several others that we'll be hearing about from Dr. Jason. Over to you, Jason. Can you let us have an insight into your company and your products that you offer? Thank you.
Good afternoon, good evening, everyone. I'm just going to share my screen. Okay, can you see my screen?
Yes, that's fine.
Okay, so yeah, good afternoon, everyone. Thanks for the introduction, ISHRE. My name is Jason Shiliday. I'm the sales manager of MSA for the HVAC range of products for the Middle East, India, Africa region, and then also some of Europe. I have a PhD in environmental technology, and I've been in the refrigeration industry quite a long time. So just really to introduce our company, MSA, we're a global leader in one of our products, which is a fixed gas and flame detection. We're headquartered in Cranbury in Pennsylvania, US, and we're quite an old company, established in 1914. So we've been in the business of safety equipment for quite a long time. Last year was a good year. We achieved about 1.4 billion in sales, and we're in a range of different industries, including the fire service, oil and gas, construction, wastewater, and industrial. So some of our core product lines are the fixed gas detection and flame detection, which we will be discussing the HVAC applications today. Then we have portable gas detectors, head protection, fall protection, we have breathing apparatus, and then we do a range of helmets for the fire and rescue service, different fire and rescue services globally. So we're headquartered in the US, but we have offices and employees spread globally to service these industries. We've a range of experts already in India and a range of good channel partners to represent our products in the Indian market. So on the agenda today, what we're going to talk about is really refrigeration leaks and leaks in mechanical rooms and places that use refrigerants. We're going to talk about refrigerants, give an overview of the leaks, and then look at the standards that are developed, safety standards to try and stop these leaks. Look at the technology that MSA has invented for refrigerant detection, and then look at how we can design mechanical rooms for refrigerant safety. So first, refrigerants. So I'm sure everybody on this call, that you're all HVAC experts, so you know that refrigerants, they can be either natural or they can be synthetic chemicals. So the natural ones being ammonia, propane, carbon dioxide, and water. And then the synthetic ones manufactured to have unique cooling capacities at different pressures and temperatures. They're all used in a vapor compression cycle to either generate cooling or heating. A leak of these gases in an enclosed space can be dangerous because there's a risk of asphyxiation. When you're breathing in a refrigerant gas, you're not breathing in air, so this can cause suffocation. And then for some of the toxic gases, it can be more dangerous, such as ammonia or R123. The leaks also cause inefficiency in the refrigerating machines. A refrigeration machine should be properly charged with the right volume of gas, or else it starts consuming more electricity. And then more recently, these large leaks can result in heavy fines due to increased refrigeration regulations in some countries. And this is happening in India with the signing of one agreement. So looking at refrigerants over time, refrigerants were invented way back in the 1920s. So the earliest ones were the CFCs, the chlorofluorocarbons. These were known then to have that chlorine atom, which damaged the ozone layer. So that was discovered in the 1980s. So very quickly, the Montreal Protocol was signed by the majority of the world to phase out these damaging chemicals. So HCFCs were invented so that they reduced the chlorine atom and brought in a hydrogen atom in order to reduce the ozone depletion potential of these gases. And then that was the like of R22, R123. Then global warming became a huge concern globally, and some of the damaging gases were refrigerants. These were invented to replace the HCFCs, so they were the HFCs, such as R134A, R404A, 407C, all common used refrigerants globally still. These were highly global warming, so the Kyoto Protocol was signed in 2006 in order to start to phase out these. And then we have more recently had the Canali Agreement in order to phase these out globally. So the newer refrigerants are the lower GWP refrigerants, the HFOs, and then we can see that the more natural refrigerants actually coming back into use much more. Propane, ammonia, and carbon dioxide are being used as gases in refrigeration systems more often because they're naturally occurring. So the agreement I was talking about was the Kigali Agreement signed in 2019. So yeah, India and where I am now, the United UAE, Dubai, signed up to this agreement. So they're form part of Article 5, Group 2. So from the years 2024 up to 2028, there will be a production freeze and usage freeze in these countries. After that, they've agreed to start reducing the amount of these refrigerants that's used and produced. So what this has happened in other countries is this has led to an increase in price because there's less of the gas available in the market. It's also made other countries switch to HFOs and natural refrigerants. So it's up to the local governments how to decide how to achieve these reductions. In Europe, they had the F-gas regulations to achieve these reductions in HFCs. So it was a quota system for each country. They were allowed to import mostly a certain volume of HFCs, depending on how damaging they were to the environment. So depending on the tons of carbon dioxide equivalent. They also had a reporting for the usage of gas on site. Engineers had to be certified to use these gases, and then there was mandatory leak checks required for each system over a certain volume. And then for large systems, leak detection must be fit. And if you had leak detection installed, you can see this diagram here. It actually reduced the number of leak tests you actually needed to do. So there was benefits to having a leak detection system installed. You can see here that the prices of the gas also increased dramatically depending on the GWP of the gas. So Our 404A had a much higher GWP on one than 134A, so the gas increased much more. Refrigerants, the type of refrigerant used actually depends on the application. So at home in your refrigerators, you could have isobutane or 600A, which is flammable, but it's used in very small quantities, and it's an extremely efficient gas. In large commercial refrigeration, large chilling industries, chillers, they still use a lot of HFCs. And then in the industrial food processing, they mostly use ammonia, carbon dioxide now, and then the large district cooling plants, which we see in the Middle East here, they use a lot of R1233 and 1234. Just to summarize about refrigerants then, yeah, so they're synthetic gases and they're oxygen depleting, so they can be deadly in high concentration. So if you're breathing in a refrigeration gas, you're not breathing in oxygen. The ammonia can be toxic and deadly in low concentrations, and we'll review that a little bit later. They're harmful to the environment and can be ozone depleting with high global warming potential, but things are changing now with these gases due to all these new agreements being signed. And the refrigerant leaks can be costly. So you have the refrigerant costs and then the increase in energy costs for the owner of the plant. So the risks we have of refrigerant leaks. So the risks of a refrigerating system leaking in your machine room or in your plant are, yeah, toxicity of ammonia mostly, or R123. You have a flammability risk of some of the more newer refrigerants. All refrigerants, you have an asphyxiation risk or suffocation risk. And then there's now environmental concerns due to the high GWP of some of the gases, the cost of gas to the owner, and the increased energy usage of the plants. So installing some kind of a system which detects the refrigerants at low levels greatly reduces all these risks to the plant operator and the owner. So we classify refrigerants in terms of the flammability and the toxicity. So this table is actually forms part of the ISHRA guidelines on safe and responsible use of refrigerants in HVAC and our systems. So you can see here for the flammability, it goes from range A to 3. So 1 to 3, 3 being the most flammable. And then for the toxicity, you have A and B. Luckily enough, most of the gases which we deal with are still in the A1 category. But with the reduction on HFCs and the move to HFOs, we're seeing a change in the higher risk due to increased flammability of these gases. So this shows you some of the new gases and really the change in the old gases as well. So you can see the ozone depletion potential actually has decreased to 0 over time. Let me just change has decreased to 0 over time. And the GWP, it's starting to come down as well. But what's happening is, you can see here, there's more red in this table. So more of these gases are getting more flammable, either with an A2 or A2L category, which increases the risk for the owner and the operator of these systems. And the designers of these systems need to be aware that these dangers are there. So leaks, where do the leaks come from, and the different types of refrigerant leaks we have? So there's standing leaks, which are leaks that can be detected when the unit is off. So all refrigeration systems turn off at some point, either on defrost when they've met temperature. So the standing leaks are best detected when the unit's off. Then we have pressure dependent leaks, which the compressor needs to be running in order to push the gas out of the system. So yeah, these are still the major leaks, that you have large volume of gases coming out of the system. And then over time, we've leaks which happen in piping or in gaskets or wells due to vibration of the compressor and fans over the time in the system. And then micro leaks occur sometimes due to corrosion in gaskets and wells, etc. So these are all sources of leaks that can happen in a system. Leaks, the majority of leaks occur in the evaporator or the condenser. This is where you have the largest surface area of material, copper usually, in order to transfer heat. So it's the highest risk areas which have gas. They also where the refrigerant changes phase from liquid to gas or gas to liquid. So there's a lot of going on in the evaporator and condenser. And then for shell and tube heat exchangers, which you can see in the photo here, you also have water on one side and refrigerant on the other side. So that can lead to corrosion from the water if maintenance doesn't happen, or there's glycol or some kind of corrosion inhibitor doesn't happen in the system. There's another photo here of a compressor completely freezing up, which can happen in an evaporator as well. So the frost or the ice would gradually push a pipe or a flange off, and then we have a complete leak in the system. So maintenance helps reduce these risks, but installing a leak detector at very, very low levels would help identify these leaks at an early stage. So the dangers of the leaks, and then what levels of leaks are dangerous. So the asphyxiation risk in an enclosed space and the toxic effects of the vapors. We have occupational exposure limits which are developed globally at certain part per million levels. So any gas leak above these levels, it becomes very dangerous to the occupants of that area. So you can see here the HFCs, the HCFCs are generally 1,000 ppm. Above that is a danger level. Some of the older refrigerants, such as R123, which is used in a lot of large water-cooled chillers, it's toxic. So 50 ppm of that is dangerous. And then we have ammonia, above 25 ppm of that starts to get dangerous. And the newer refrigerants, because of the flammability issues, yeah, you need to be able to detect them at low level. So the only way of detecting if this level of gas is in your plant room is to install some form of leak detector to check the ppm levels of that area. So in order for you not to get to the high level 1,000, you would have different alarm levels, maybe at 50 or 250. So you can detect the leak at a very early stage and fix it before it gets to these levels. Ammonia, of course, is used in lots of other industries. So there's lots of studies done on the risks of ammonia. So you can see here, above 20 ppm starts to get the mild discomfort, and then large leaks of an evaporator that's had a big leak up to 300 ppm start to have damage on the respiratory system. So it's very important these are detected very early if these are used in a large food processing area, for example. So there have been a lot of leaks in ammonia systems and even in some of the HFC systems globally. So all over the world, so in the UK, there's been a number of ammonia leaks, some in the food processing at Carlsberg Brewery, and then also in a fertilizer plant. And then an ice skating arena in Canada. And then in India, more recently, there's been some accidents. There was a large explosion in a cold storage facility in Lucknow, and then there was an ammonia leak in a processing factory in Goa. Unfortunately, there was a death of 3 people due to asphyxiation in Chennai due to a leak from an air conditioning system. So this must have leaked into a small enclosed room, and the refrigerants are heavier than air except for ammonia, so they will go to the floor where people are sleeping. So this is one of the dangers and why leak detection is necessary for safety. So the refrigerant safety standards we have, there's 3 main standards. We have the ISRA guidelines, then we have ISO 5149 standard about refrigerant safety, which is based on the EN 378. And then we have the ASHRAE 15 standard, which also links into ASHRAE 34. ASHRAE 34 describes the refrigerants and gives the safety properties of the gases. So the ISRA guidelines, so that this is a this is a screenshot just of the front of the ISRA guidelines. So it discusses the international standard, that the ISO 5149, and it states that all machinery rooms are required to have a mechanical ventilation system controlled by oxygen deficiency alarms or refrigerant vapor alarms. So oxygen deficiency alarms is an oxygen detector. So if the refrigerant, the mass of refrigerant in the room is more than the oxygen, the levels of oxygen in the room will start to decrease and become dangerous for people to breathe in there. But at this stage, it's really too late. So it's much better installing a leak detection system that detects the actual refrigerant at a very early stage than an oxygen deficiency system. So the other ISRA guideline is it's a more recent one. That one, it was the guideline 25149, and this is just a screenshot off the front of the guideline. So it says refrigerant detectors play an important role in the safety procedure for people and personnel, and it highlights that in Chapter 9 of the ISO guide, it shows the set values, delays, actions that is needed to design the system properly, and it focuses on the new flammable refrigerant and R717. Then we have the international standard, ISO 5149, which is based on one of the European standards, EN 378. So it sets concentration limits for the gases in the document. So if there is a risk that concentration limit could increase above the concentration limit, then a refrigerant alarm is needed to alert inside and outside the room and to activate the mechanical ventilation system. So most of these guidelines want a ventilation system. You have to alert a responsible personnel, alert inside the room, and then activate a mechanical ventilation system to remove the dangerous gas from the room. Then we have ASHRAE 15, which is a standard which is used quite a lot where I am in the Middle East, in Dubai, for a lot of the plant rooms. So it says that if there is a refrigerant in the room, in a refrigerating machinery room, a detector must be installed. And it highlights a lot of other different things in terms of self-contained breathing apparatus, and the alarm needs to be visual and audible inside the room and both outside the room. So a lot of the specifications we get in the Middle East just say that the refrigeration room must comply with ASHRAE 15. Then we know we need to put some kind of refrigeration detector in that room to detect the leakage of the gas from the chiller. This was updated in 2019 quite recently, just to change some things in the standard due to the introduction of the flammable refrigerant. So there's different discussions in this document in order what to do with the A2L gases as well. Then we have separate safety standards for ammonia. So there's quite a lot to read here. So it's just highlighted the main points that this standard, so the EN 378 ISO 5149 says you need to put at least one detector over the compressors. So because ammonia it's lighter than air, so it goes to the ceiling. A detector over the compressors will detect that gas, because the compressor is the thing that vibrating the most and is one of the areas you're most likely going to get a leak. There also needs to be 2 alarm levels. So you have a low level alarm at 200 ppm. So then the mechanical ventilation needs to be activated. Then at very high levels, so 30,000 ppm, it initiates a shutdown of the system, because at those levels it starts to get flammability issues. That's usually a large discharge of gas in the plant room. But if it gets to 200, if you have the early level leak detector at 200 ppm, you're going to know something is happening before the main alarm happens. So early leak detection is very important in these systems. And then we have the American standard for ammonia, which is ANSI IIAR2. Again, it's similar. In the plant room, you need to have 2 detectors at different levels. And the levels are a little bit higher, but it just says not exceeding 1000 ppm. And then it needs to be de-energized everything at 40,000 ppm. And the locations of the detectors and the visual and audible alarms are the same as the other standards. So they follow a common theme in the ammonia industry because of how dangerous the gas is. And then we have the occupation exposure limits to ammonia. So where you have people working in a food processing plant that's using a direct expansion or a flooded ammonia system, you need detection levels down to 25 ppm where those people are working. Ammonia has an inbuilt warning in the smell of it, and so is propane and some of the other gases, so you will know it's there, but the HFCs, they don't have this smell added to it, so that's why sometimes they can be more dangerous. So safety standards, a summary on the standards. So all of the international standards actually call for leak detection in the mechanical rooms at least. So ISHRAE and ASHRAE say it needs to be installed in the mechanical rooms where refrigerant is present. And then ISO 5149 calls for leak detection in occupied room if there's a risk of the leak going above the refrigeration concentration level, which is in the document ISO 5149. So down to what MSA does. So we manufacture gas detectors, the sensors and the transmitters and the controllers. It's a big part of our business globally. We do a lot in the oil and gas industry and pharmaceutical industry, and we do a lot in the HVAC industry for leak detectors for plant rooms as well. So there's really 3 different ways of detecting ammonia for different industries. We have a sampling system, the ChillGuard 5000, which is the majority of HVAC applications globally for R134A and for R123 and the new refrigerants. Then we have open path detection. Now, it's not really used for HVAC too much, but I thought it would be interesting to show ISHRAE that the other types of ammonia detection systems we use. And then we have a point detector, which is the normal way of detecting gases, but ours is a little bit different than other detectors, so it's called the X5000. So the first method of detection we use is our sampling system. So a sampling system contains a pump, and what it does, it collects samples from different locations around a plant room through some form of tubing, whether the tubing is polyurethane, copper, or it can be stainless steel for some pharma applications. So the tubing is distributed in the plant room, and then we have a pump which sucks the samples into the sensor, and then the sensor will analyze the gas to see if there's ammonia or any other type of refrigerant in it. If it detects the gas, then we get an alarm on top, or we get signals out to alert the facilities manager that, yeah, there's a gas leak at that particular location. So for the ChillGuard 5000, the Freon model has 39 different gases on it, and we can add new gases to it. So the important thing to notice here, that there's only one sensor. So we only need one sensor in this model. So a typical plant room would look like this image here. We have the sampling system, the ChillGuard 5000 on the wall, and we have all the tubing which goes into these here nozzles on the side or the bottom of the casing. So there can be up to 16 different locations in the plant room. So they're installed they go generally underneath the floor, or they can go on top of the floor and the roof, but they're installed at the base of the chiller. And they have a filter at the end which filters out any of the dust or anything around the base of the chiller. So it sequentially samples different points. So every 14 seconds, it will take suction from one sample, then it will move on to the next, then it moves on to the next. So you can get much wider range of detection than putting, one sensor. So only one sensor is needed for a large 16-point area. So sampling technology is different than electrochemical sensing technology, because if we were using point detectors, we would have to have, for this example, 1, 2, 3, 4, 5, 6, 7 separate detectors with 7 separate sensors. But in a sampling system, it's just one sensor connected through tubing to each of these different locations. So only one calibration annually is required, where for the point detectors, for this example, you would need 7 different calibrations. And when it came to replacing the sensors, 7 different sensors would need to be replaced. So there is some cost savings. We'll go for the sampling system as well. For the ammonia applications, because the sensors are stalled at height, it's much better a sampling system, because the sensor is stalled at the head height, where the sample is taken from the ceiling. So this is the other example of ammonia. So it's mostly ammonia production, where we need to protect the boundary of the ammonia facilities. They're large facilities, and they want to know if there's a leak in a large area. So what we have for it, we have our open path gas detection system. So it's a gas detection system which has an infrared or laser beam. You have a source and a receiver up till about 120 meters apart. And these will only alarm when one particular kind of gas is present, because false alarms are a huge issue for large facilities. They're very expensive, and they can be, they're dangerous as well. So if a gas cloud or a small part of the gas was to go between these beams, an alarm would happen, and the alarm happens very, very quickly. It's less than 3 seconds in order to detect the ammonia leak from these systems. So they protect boundaries of large ammonia plants, and they could be used for large cold stores for ammonia detection in food processing areas if required. So one system can detect 50 meters, but for point detectors, you may need 10 or 15 point detectors and 10 or 15 sensors. So they have huge benefits over point detectors, but you always need to have different kinds of detection in one system. So this is an image of ammonia storage monitoring. I can't remember which country this is in, but you can see here what they're trying to protect is a leak from this horizontal ammonia storage tank. So we have the transmitter, the source, and then we have the receiver about 20 to 30 meters away. So that is protecting from an ammonia leak in this area. And of course, this type of system can be used for a majority of combustible and toxic gases. So it's not just for ammonia. We use this in the oil and gas industry as well for boundary protecting of sites. And then the final type of gas detection technology we have is the traditional point detector, where it's a dispersive type. So the gas needs to come to the base of the sensor in order to be detected. So our point detector is the X5000, and it has a range of benefits compared to other competitors. We give a 3-year warranty, and there's a long cost of ownership. There's a lower cost of ownership with this because the sensors are extremely long lasting. The sensors are always reacting with air, so over time, they do degrade. So sensor replacement is a major thing in the gas industry. So this product enables a much longer lifetime of sensors, which is important in ammonia detection, because often the point detectors are difficult to get to because they're at high level. So this is a summary really of the 3 types of gas detection system we offer, for ammonia and sometimes for the other gases. For HFCs, it's HFCs and freons. It's mostly the Chilgard 5000, but for the ammonia and any of the other more dangerous gases, we can offer the open path gas detection, or we can offer our long life X5000 point detector. So how do we design these mechanical rooms for refrigerant safety? So for a typical water-cooled chiller room, where we have So in this example, we have three large centrifugal chillers, but I have some plant rooms, in the Middle East here where they have 16 or 17 large centrifugal chillers. So they're big plant rooms. So the detectors always should be at the base of the chiller if it's in the HFC, because if there's a leak, the leak will always go to the ground. So the base of the chiller where the leak is going to happen. And this is an enclosed space. So anything that leaks in a water-cooled chiller room, the leak will stay in the room because there's refrigerant stays in the room. Only water goes in and out. So 1 or 2 points per chiller at least installed at the base of the chiller. Then we need to have an alarm inside the room, and we need to have an alarm at the doorways as well. And what ASHRAE calls for, it actually calls for some self-contained breathing apparatus as well, that if somebody is unconscious, somebody needs to wear that apparatus in order to retrieve that person outside. It's important also to put a detector in the refrigerant storage area if there's a leak there. So the system should also be detected to the local, or connected to the local SCADA or BMS system to alert the user remotely that there is a leak. If we can detect at very low levels, which we do with the chill guard at 1 ppm, you can prevent a small leak going into a much larger leak for the operator. So at the doorway, we have the alarm system. We have a siren. We have different light warnings for the level of the leak. And then we have a display here as well, which the operator can see if there's the gas levels at different locations in the room. Then we also have a self-contained breathing apparatus here. So ammonia system is slightly different only because the gas goes to the ceiling. So this is a typical ammonia chiller room. So the ChillGuard 5000 is still located on the wall, but all of the detection points then are at high level at the ceiling. So this is hugely beneficial for calibrating and maintenance, because all of the maintenance actually happens at the wall here at the refrigeration monitor. The only thing that needs to happen is a filter at the end needs to change. So 1 point for compressor for a flooded or DX ammonia system. And then we need 1 point as well for high level shutoff as per the standards. Alarm inside, alarm outside, and then of course connected to the central BMS system to let the main operator know there's a leak. And then for a food production facility, which has a DX or flooded ammonia system, so there's ammonia distributed throughout the plant. For a glycol system, you wouldn't really need this. You would only need ammonia detectors in the plant room. So again, we could have a number of the chill guards distributed among the areas where there are occupants. So we have the tubing, which is different tubing for ammonia. It could be stainless steel or a different type of polyurethane. And it's located at the ceiling, and then it's all sent the information back to the control room to alert the user if there's an alarm. So these areas, the production areas, they would need to be a 25 ppm alarm. And then the plant room would need to be, it would be good to have 25 ppm, then 200 ppm, and then complete shutdown at that 30,000 or 40,000 ppm. So in summary of the presentation regarding leak detection, refrigerant leaks, they can be dangerous and expensive for plant operators and owners. Further restrictions in the use of HFCs in India, it will increase the prices like it has done in Europe and the US, and it will initiate a switch to the more environmentally friendly refrigerants, which have this flammability risk. So you want to keep the gases in the system or install some kind of detection system. So consultants and designers should be looking at these, looking at the evolution of gases and considering these changes for new refrigeration systems, because yeah, refrigeration systems now last 20, 25 years. So what happens is the gases may not be available, in another 10, 15 years. So they should make the system with a new gas, or be able to switch the gas to a new refrigerant. So all of the international standards call for some form of refrigerant leak detection in the mechanical rooms, at least. So we at MSA, we're experts in gas detection, so we're happy to take any questions on this topic, and we have experts in the field in India, which we can discuss with any of you at any time. It's also important to note that a leak detection system is a very small item compared to the cost of a full refrigeration plant. And the cost of this actually can be recovered by saving refrigeration gas. It also leads to a better performing system and a much safer refrigeration system and a much safer plant for the owner and the operator. Okay, thank you everybody for listening. I hope